Next, let us look at the sources of uncertainty. We will discuss 5 sources of uncertainty: the model structure, the model technical uncertainty, measurement errors, the model input, and the model parameters. Let us first look at the uncertainty in the model structure. As we have already mentioned a couple of times, every mathematical model is only an approximative representation of the reality. Since this model will never be completely exact, so we cannot capture all the details in our mathematical model, there will be inherent errors. Different models or different model structures will differ in different aspects. These aspects in which the model structures differ are the state variables, the processes that we are considering, the complexity of the equations, and the number of independent variables. This uncertainty is very difficult to quantify, not in the least because we do not know the exact model, so we also don't know which errors we are making with respect to the reality. Nevertheless, there can be indications that the model structure that we are using is incomplete. A first indication that there is something wrong with the model structure might be the existence of patterns in the residuals. Another thing that can point to problems with your model structure is that if you calculate your parameters or you estimate your parameters with different training data, that you get large variations in these estimations. Because of the stochastic nature of the data, of the training data, you will always expect to see some small variations in the estimation of the model parameters. But if you see that there are very huge fluctuations, if you estimate them using different data sets, then there might be a problem. One option to solve this problem, or at least to reduce the model structure uncertainty, is to create alternative model candidates for the same system. So you will create a model ensemble, you will think out different scenarios, different model candidates, and you will compare them, you will see how things evolve, what happens for each of those models. The comparison between those different models is usually done through the mean and the standard deviation. The mean and the standard deviation which you obtain through model simulations. Using the mean and the standard deviation, you get then an idea of the uncertainty of each of the models, and then you can choose the model with the least uncertainty. The problem with this solution is, did we propose sufficient alternative models? So did we think of all the plausible alternatives, or are there other alternative models that we need to consider? An example is the one we saw before with the global surface warming. Here, 4 different scenarios have been created, 4 different models have been created. For each of them, we calculated the mean through simulations and the standard deviations, and then using the standard deviation, you create the uncertainty band around each of those means. A second source of uncertainty is the model technical uncertainty. This uncertainty is caused by the implementation of the model, so by the coding of your model through a computer program. When executing the program, you will make numerical approximations, so you will never have an exact calculation, and there can also be software bugs. Software is never perfect. In reality, this type of uncertainty is often underestimated or even totally neglected. You can try to reduce this type of uncertainty using a critical quality control of your found solution. So you could implement the model by several modelers. This will lessen the bugs. You can implement the model on different software platforms to see which of those platforms is most reliable or most stable. And you can try to use multiple numerical algorithms to solve the model, or you can use different settings to solve the model, and then you can see which of those gives the least uncertainty. Next, there is the measurement error uncertainty. Naturally, with every measurement, you also make a measurement error. In an offline setting, an offline measurement, so a real-life physical measurement of a quantity, these uncertainties come from the sampling or the sample treatment. They can stem from the measurement protocol, or they can be through human errors or human imprecisions. In online measurements, the placement of your sensor can have an influence. There will always be some noise on your data. The calibration is never perfect, or the resolution can have an influence. Often the measurement error is expressed as a standard deviation which you can either calculate or you can find it in the manual of your measurement tool. Measurements, they are used to calibrate the model, so they are used to estimate the parameters of the model, and these measurements, they are susceptible to measurement errors. And if we have measurement errors in the measurements to calibrate the model, there will also logically be errors in the estimated parameters. Also the model input, so what we put into the model are often measurements. And so if we make errors in these measurements, these errors go into the model and then they are propagated through the model and they come out as errors on the output of the model. Then fourth, there is the model input uncertainty. When we want to make predictions using our model, we need to input data into the model. We already said in the previous point that for these inputs there are also measurement errors, but it is often also difficult to predict what exactly the future input of your system will be. For example, for global climate change, how will the climate evolve? Or what will the CO2 emissions be in the future? We have no idea how this will go. In water purification, how do the production and the composition of the wastewater evolve? So all of those things, they have an uncertainty. We don't know what will happen in the future. And so we can only make a guess of what will happen in the future and what model inputs we will need to use to make the predictions. A possible solution again is to think out different scenarios, so different possibilities for the future. And that way we create a model for the input system. So we create a model for possible inputs in our system. If we take again the example for the global surface warming, what we see is that for the future we have considered 4 different models, so 4 possible scenarios for the inputs. And then the fifth source is the model parameter uncertainty. We know that each parameter is only an estimation through the data, so we use our training data to estimate the parameter values. But such a parameter estimation is a lot more useful if it is accompanied by confidence intervals. So if we know what the plausible values are for this parameter. In this case, we have a spread on the parameter estimation, and this spread, this uncertainty, can be propagated to the output, so it can be calculated through the model to see what happens at the output level.